Hello everyone, today let's take a look at QB135, relatively tricky question, in which part A, we're proving the hockey stick identity right here with the committee forming argument. And then part B, we're going to use that to set up and evaluate a sum that counts the number of ways to distribute 12 identical candies to 4 children. Alright, first things first, in part A, let's understand what this formula is saying by looking at an example. So I'm going to just take maybe the example of 7 choose 3. So 7 is going to be my n+1 term, and 3 is going to be my r+1 term. Then on the left-hand side of the equation, we're iterating from r. In our case, we had r+1 equal to 3, so r from 2 all the way up to n. In this case, we have n equal to 6 because our n+1 was equal to 7. And unlike with Pascal's identity, now the terms that we are adding have the iterator in the top. In Pascal's identity, we had iterator in the bottom. So in our example, 7 choose 3, our k is going to start at r, which is going to be 2. And then on the bottom, we're going to have r as well for our first term. So 2 choose 2, and then we're going to keep on iterating up through 6. So plus 3 choose 2, plus 4 choose 2, plus 5 choose 2, and then plus 6 choose 2. This is what the hockey stick identity is saying for this example. Now, how does this make sense as a committee forming argument? Well, imagine I have my 7 people right here represented by these circles. Is that 7? Yes, it is. So on the left-hand side, I'm counting the number of committees that I can form of 3 people. So for instance, this would be one committee, this would be one committee, maybe this one, etc. So then on the right-hand side, what am I saying? Well, first of all, I'm saying 2 choose 2. So I'm just basically breaking my group up into a group of 2 people, and then I'm leaving these remaining 5 people over here. So I have 2 choose 2, and there's going to be one way to form that committee, right? 2 choose 2 is 1. But I know I'm trying to form committees of size 3, so by choosing 2 here, I'm basically leaving room for one extra person. So let's just say it was this extra person that I'm leaving room for. Okay, so now I've formed a committee from these 3 specific people, which I've counted 1 time. So in the committee that I formed down here, these 4 people are excluded. So that's what's being counted in this 2 choose 2 term. But now let's look at this 3 choose 2 term and try to figure out what that could mean. So I've counted the number of committees for these 3 specific people down here, and this might be a little bit unintuitive, but basically what we can do next is choose 2 of these people from that group, right? And then choose one more person that we were previously excluding to be with the committees that we formed from there. And in doing that, we've counted the number of committees that include this person but exclude these 3 people over here. That's what's being counted in this 3 choose 2 term. So basically by summing 2 choose 2 and 3 choose 2, what have we counted? Well, we've just counted the number of committees that we can form of 3 people from this group right here of 4 specific people, these 4 specific people, and excluding these 3 people up here. So in this 2 choose 2 term, we counted the number of committees of 3 that we could form from these 3 specific people right here. Why? We just applied Pascal's identity. We know that by Pascal's identity, 3 choose 3 is just going to be equal to 2 choose 3 plus 2 choose 2, right? And 2 choose 3 is meaningless, it's 0. And then the 3 choose 2 term was counting the number of committees that came from this group of 4 people such that this person right here would be included. So when you add these 2 terms here, 2 choose 2 plus 3 choose 2, what you are doing is essentially counting the number of committees of 3 that you can form from this specific group of 4 people. The number of ways to do that is 4 choose 3, which is going to be equal to the sum of these 2 terms. Why? Because, well, by Pascal's identity, this is equal to 3 choose 2 plus 3 choose 3, and then we basically just applied Pascal's identity again to this term right here, because 3 choose 3 is equal to 0 plus 2 choose 2, so we can just replace this with 2 choose 2. Okay, so now let's keep going. We know that the sum of those 2 terms is just equal to 4 choose 3. Now let me make some room by getting rid of all of these drawings right here. Let's see if I can do it. Get rid of this. Okay. Now the next logical thing you do, once you've counted the number of committees of 3 that we can form from these specific 4 people, we're going to need to add in our remaining people. So let's choose 2 people from this group of 4, and then let's add in this person to be our third. So now this term right here, 4 choose 2, now counts the total number of committees such that this one is included and these 2 are excluded. So this term 4 choose 3 from before, which was just the sum of these 2, counted the number of committees we could form from this group of 4, and then this term right here counts the number of committees that we can form such that this one is included and 2 are chosen from here. So when we add these 2 together, 4 choose 3 plus 4 choose 2, that's going to be the total number of committees that we can form from this group of 5. Again, that's another direct application of Pascal. 4 choose 3 plus 4 choose 2 is just going to be 5 choose 3 by Pascal, the number of ways to choose a committee of 3 from a group of 5. So again, sorry if I'm being redundant here, but in the first 3 terms that we've calculated, these 3 right here, we've calculated the number of ways to form a committee of 3 from these 5 specific people right here, where these 2 up here are excluded. Okay, now what's the next logical step? Well, let's choose 2 people from this group of 5 that we have down here. The number of ways to do so is 5 choose 2, and then we're going to be leaving room for one extra person to join the committee, one that we have previously excluded. So in this term, we've calculated the number of committees that include this person but exclude include this person. You can really see the pattern in this term right here, which was collectively the sum of these three up here. We calculated the number of committees formed from these 5 specific people. In this term right here, we calculated the number of committees formed from this person plus 2 people from this committee. So when we add these two up, again, Pascal's identity, we're counting the total number of ways to form a committee from these 6 people right here. Why? Because Pascal's identity, 5 choose 3 plus 5 choose 2, is just going to be equal to 6 choose 3. Therefore, the first 4 terms right here collectively sum up to 6 choose 3. And now you see the pattern, so we can do our final step. So in the first 4 terms, I calculated the number of committees that I can form from these 6 people here. So now I need to calculate the number of committees that include our final person, our 7th person. So I need to choose 2 people from my group of 6 so I can leave room for my 7th person. The number of ways to do so are 6 choose 2. So again, one more time, 6 choose 3 was the number of ways to form a committee of 3 from this specific group of 6. 6 choose 2 is the number of ways to form a committee such that this person right here has to be included. So when we sum these up, we're going to get the total number of committees that we can form from this group of 7. And that's just another application of Pascal. We previously computed that these first 4 terms were summing up to 6 choose 3. So when we add on 6 choose 2, again, that is just 7 choose 3 by Pascal. So we just showed that these 5 terms sum up to 7 choose 3, exactly what we wanted to show. We were using committee forming argument. It was pretty in-depth. This whole formula is kind of repeated applications of Pascal, right? I start with 7 choose 3. I can break that down into 6 choose 3 and 6 choose 2 by Pascal. Then I can break this term down into 5 choose 2 and 5 choose 3 by Pascal. I break this one down into 4 choose 2 and 4 choose 3 by Pascal, which I break down into 3 choose 2 and 3 choose 3, and then I broke down 3 choose 3 into 2 choose 2. So to generalize, what am I doing? Well, if I have n plus 1 choose r plus 1, then I Pascal break that down into n choose r plus n choose r plus 1, that's just Pascal. Then I can Pascal break down this term recursively into n minus 1 choose r plus n minus 1 choose r plus 1. Then I Pascal this one into n minus 2 choose r plus n minus 2 choose r plus 1, and I just keep on going. And then I keep on going like this, breaking down the term with an r plus 1 in the bottom until it doesn't even make sense anymore. For instance, when this one drops below the value of this one, this term will always be 0, right? So eventually it's going to stop. So the final term in my sequence is going to be r choose r, and you can see that that is exactly what is encoded in this summation right here. Now, one more thing, if we actually look at Pascal's triangle, we look at our term right here. This was 7 choose 3 encoded in Pascal's triangle. We found that by the hockey stick, this 7 choose 3 is going to be equal to 6 choose 2 plus 5 choose 2 plus 4 choose 2 plus 3 choose 2 plus 2 choose 2 right here. Now you can see why it's called the hockey stick, because this shape right here looks like a hockey stick, right? These terms here sum up to this one. And that's going to be true of any number on the triangle. For instance, this one right here is the sum of 1 plus 1 plus 1 plus 1 plus 1 plus 1. 6 is the sum of 6 ones, obviously. Now 5 is the sum of these 5 ones before it, right? 15 is the sum of 10 plus 4 plus 1, right? They're all hockey sticks. And finally, one more time, why is that true? Well, we basically are applying Pascal's identity recursively is what we found. So what does that look like on this chart? Well, we know that by this Pascal stuff up here that we were doing in QP 109, right? If we have 7 choose 3, well, that's the sum of these 2 terms right here. So this one plus this one over here, but we can break this term down, right? This 20 down into its 2 terms, which are going to be 10 and 10. Then we can break this 10 down again into its 2 terms, which are 6 and 4. Then we can break this 4 down into 3 and 1. Then we can break this 1 down into just this 1 right here. So that's how you get the hockey stick. All right, that part A went a little bit longer than expected, but now in part B, we need to use this identity to find a hockey stick sum that counts the number of ways to distribute 12 identical candies to 4 distinct children. Distinct is implied. You could very easily use stars and bars to solve this, right? It would just be 15 choose 3, but the point is with this question to not use stars and bars, to use the hockey stick sum. We're going to be using a lot of stars and bars later, and you can see that it's going to be a lot harder if we're not allowed to use stars and bars. Without using stars and bars, this one's pretty hard to come up with intuitively. Basically, what you have to do is just start from a very simplified version and then work your way up. So let's start with 0 candies and 1 child. How many ways can I distribute 0 candies to 1 child? Obviously, 1 way. Now, how many ways can I distribute 1 candy to 1 child? Well, obviously, just 1 way. I can give them the whole candy. Now, how many ways can I distribute 2 candies to 1 child? 1 way. So in general, the number of ways to distribute n candies to 1 child is going to be 1. All right, now let's work our way up. What about when we have 2 children? So I have 2 different children. How many ways can I distribute 1 candy to 2 children? Maybe you can see where the hockey stick's going to come in. We can either choose to give the first child a candy or not give him a candy, right? So our possible options are not give the first child a candy and give the second child a candy, or give the first child a candy and don't give the second child a candy. So we have two different options for that. So for one candy, two children, we have two different options. Now let's look at when we have two candies and two children. So for my first child, I could choose to give them 0, 1, or 2 candies. So I have 3 different options for my first child. And once I've chosen how many candies I'm going to give to my first child, well, then I'm just going to give the rest to my second child. So I'm only going to have one way to do that. So I'm going to have, when I have 2 candies and 2 children, I have 3 ways to distribute my candies. Now you can see the pattern. When I have 3 candies and 2 children, well, then I'm going to have 4 options for my first child, 0, 1, 2, or 3. And then I'm going to give the remainder to my second child. So 4 options, right? For 3 candies, 4 options. Now you can see in general for n candies, I'm going to have n plus 1 different options for my first child, right? 0 through n. And then I'm going to have 1 for my second child because I'm just going to give them the remainder of the candy. So for n candies and 2 children, I'm going to have n plus 1 different ways to distribute them. Okay, so now we're working our way up. Let's do 1 candy given out to 3 children. Try to find a pattern. Well, I can either give this first child a candy or not give him a candy. Now, if I choose not to give him a candy, well, then notice that we're back in the situation up here, so we kind of recursed. So since I didn't give this child a candy, I'm going to have 1 candy to distribute to 2 children, which I'm going to have 1 plus 1 ways of doing so. So 2 ways for this combination where I don't give the first child a candy. But now if I do give the first child a candy, well, then I'm going to have 0 candies to distribute to 2 children, which I can do in 0 plus 1 equals 1 way. So I'm going to have 3 total ways to do 1 candy to 3 children. Okay, now let's think about the situation where we have 2 candies and we are distributing them to 3 children. So if I choose not to give the first child a candy, well, then I'm distributing 2 candies to 2 children, which I can do in 3 different ways. If I do choose to give the first child a candy, well, then I'm distributing 1 candy to 2 children, which I can do in 2 different ways. And if I do not, or if I give the first child 2 candies, well, then I'm going to have 1 way to distribute 0 candies to the remaining 2 children. So 3 plus 2 plus 1. Now the pattern's pretty clear. If I have 3 candies and I give the first child 0, well, then I have 3 candies to distribute to 2 children. I can distribute 3 candies to 2 children in 3 plus 1 ways, so 4 different ways. Now if I give the first child 1 candy, I'm going to have 2 candies to distribute to 2 children. We already calculated there's 3 ways to do that. Now if I give the first child 2 candies, I'm going to have 1 candy to distribute to 2 children. There are 2 ways to do that. Now if I give the first child 3 candies, well, there's going to be 1 way to distribute 0 candies to 2 children, so I add on a 1 here. So again, the general pattern is now going to be obvious. If I have n different candies, well, then the number of ways to distribute them to 3 children is going to be n plus 1 plus n minus 1, etc., all the way down to 1. We can find a shorthand version for this sum right here from QP65. It's funny because in that video I was talking about using the hockey stick identity to prove part B of that, and now I'm talking about using part A from that video to prove part B of this one. But we know the formula for this is just going to be n plus 1 times n plus 2, all of that divided by 2 from QP65 again. This is just equal to n plus 2 choose 2 as well, right? So we found our formula for 3 children, 2 children, and 1 child. So now let's do it for 4 children, which is actually what we want, so we can solve the actual question that we were given. So now 1 candy and 4 children, I can just use the same strat that I've been doing. If I give the first child 0 candies, well, then I'm going to have 1 candy to distribute to 3 different children, which I can do in this many ways where n is equal to 1. So there's going to be 3 different ways that I can do that. If I do choose to give the child a candy, well, then I'm going to have 0 candies to distribute to 3 children. If I plug in a 0 here, I get 2 choose 2, which is 1. So when I add on 1, I get 4. So for my first one, I have 4. Now 2 candies to 4 children. If I choose not to give the first child a candy, I have 2 candies to distribute to 4 children. If I plug into up here to my formula, I get 4 choose 2, which is equal to 6. If I choose to give the first child 1 candy, well, then I'm going to have 1 candy to distribute to 3 children. If I plug in 1, again, I get 3 here, which we've already calculated. And when I give the child 2 candies, well, then I'm going to get this term right here, which again, we've already calculated. So you can see the recursive nature of this. This is going to be equal to 10 in the case of 2 candies. So I'll put 10 here. So even after 2 candies, again, it's pretty obvious. We're just recursing. Right here, we're plugging into this formula n equals 2. Then we're plugging into this formula n equals 1. Then we're plugging into this formula n equals 0. So the general form for n is going to be pretty obvious. So let's just write it out immediately. For n candies to 4 children, what is our formula going to be? Well, we're just taking the sum from k equals 0 to n, basically, of k plus 2, choose 2, because we're just using this formula for all of our terms and summing them up like I just showed. If we expand this out, you can see the hockey stick that we just did is going to be equal to 2, choose 2, plus 3, choose 2, plus 4, choose 2, dot, 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 all the way up to n plus 2, choose 2. And we know that by hockey stick, this is just going to be equal to, well, we have to increment this top one by 1 and the bottom one by 1. It's going to be equal to n plus 3, choose 3. So in our case, when we have 12 candies, that's our n value. It's going to be equal to 15, choose 3. Look at that. It's exactly the stars and bars formula. So that's how you get the stars and bars formula, basically. So that's pretty cool, huh? But now can we generalize to n candies and n children? That's going to be our final challenge. Well, first, let me just do it for 5 children. Well, for n candies to 5 children, you can pretty clearly see it's just going to be the sum of all of these. It's just going to be the sum from k equals 1 to n of n plus, or sorry, k plus 3, choose 3 now. And we can hockey stick again. That's just going to be equal to n plus 4, choose 4. So now again, you can see the pattern emerging. This one right here is going to be 1 minus the number of children that we have, like it was here, right? 4 minus 1 is 3. Now let's generalize one more time. For n candies and m children, our formula is going to be the number of ways to distribute these candies to the m children is going to be n plus k minus 1, choose k minus 1, exactly the stars and bars formula. And we used hockey stick to prove that by starting at base examples. It's always easiest when you start from your base cases and work your way up and try to find some pattern. In this case, we did so with the hockey stick. So yeah, that was a pretty long video, huh?